problem what it is. Uniform cylinder of length L and mass M is having a cross-sectional area A suspended with a vertical from a fixed point of a mass by a massless spring such that half of it is immersed in a liquid of density rho at an equilibrium position. Quite a long sentence, right? So let me try to put this into the format of a diagram and try to draw what is given for you. Yeah. There is a uniform cylinder. So let me draw a small cylinder first. Of total length L, mass M, cross-sectional area A, suspended with its length vertical. So that's why I have drawn a vertical cylinder. It is vertical in my diagram. From a fixed point, it is suspended from a fixed point. Let me call this as my that fixed point by a massless spring. So we are using a spring for suspension. So this is the spring that I'm talking about. Its mass is ignored. It's a massless spring as for the given problem, such that of the total length L, half of the length is immersed in a fluid. The fluid is having a density rho. That's what given for you, right? Now, what he's saying is when the cylinder is given a small downward push and then released. So, what he's saying is this cylinder is given a small downward push like this, a small downward push. It starts oscillating vertically with a small amplitude. So, this is having a kind of a oscillation. Up and down, it is oscillating. That cylinder is oscillating. If force constant of that spring, the spring spring is equal to K. So we are having that spring is having a force constant K. What is the frequency of oscillation is? So what is the frequency of this oscillation is the kind of a question. So first thing that we would like to understand is, would like to just consider is, it is given that when it is slightly disturbed, when it is pulled little down, that's what is said. It's given a small downward push and released. So when you pull it this way, the entire system gets displaced, right? So it moves up and down. Let that value is happened by a value x. We don't know, I'm just assuming it like x. Let send get displaced vertically by a value. So when it is pulled down, it goes back. Its oscillatory motion means what? It's going to go back. So who is pulling it back? There is some force that is pulling it back, which is called as restoring force. But be careful. This restoring force comes due to two reasons. One, due to the spring. Another, due to the upthrust of the liquid. So there are two forces acting. Upthrust, this liquid always being in a fluid, it always applies the force called upthrust. So the system is coming back to its original position even when we have slightly disturbed because of two reasons. That combination is called upthrust. So what we can say, restoring force is a combination of restoring force of spring that is there plus upthrust of the liquid. So restoring force can be written like this restoring force is coming to this cylinder. So I can call force or mass into acceleration. I can of course write a minus sign because these two are acting in opposite direction, right? So the applied pull, these two are acting in opposite direction. So I can consider like they are in opposite direction. So I can write a minus sign equal to minus of, restoring force of a spring is Kx. We know the formula. For a spring, force is directly proportional to displacement. So F is equal to minus Kx. We know that's a restoring force plus upthrust for a small displacement of x. The formula for the upthrust is volume of the fluid displaced, density of the fluid into acceleration due to gravity. So minus kx. Volume of the fluid can be written like area of the fluid displaced, length of the fluid displaced, density of the fluid, and acceleration due to gravity. So that is minus of kx plus area of the fluid displaced is the entire area itself because that's given for you. Area of the cylinder is A. Length of the fluid displaced is x because it's only the displacement, not the entire part of the cylinder is displaced. Only a portion of the spring, that is x, is displaced this much. Density of the fluid is given for you as rho and g value is g itself. From here, I can write acceleration as minus. I can take, of course, x common, so k plus a rho g of x by mass. That's what's the equation for the acceleration. So if you observe this equation little carefully, it's an equation for acceleration of a particle in simple harmonic motion. K is a constant, area is constant, rho is constant, g is constant, m is constant. So what all is here is a constant value. So what we can say, right, because that's all is a constant, acceleration equal to, if you leave that constant, there is a negative sign and there is displacement. So what is the understanding of that? Acceleration is directly proportional to minus x because what all is given here is a constant value. What all you have got is a constant value. Acceleration directly proportional to displacement. Having a negative sign says that it is in opposite direction, acceleration and displacement. Therefore, we can say entire system is a simple harmonic motion. So I can write A that is similar to A equal to minus omega square x that we have derived. That is the simple harmonic motion. So how much is omega square is? Whatever you have found like a constant, omega square equal to k plus A rho g by m. So omega will be under square root of that k plus A rho g by m. We know omega equal to 2 pi by t, or 2 pi into 1 by t is nothing but frequency, equal to k plus A rho g by m. That implies, as you want the frequency of oscillation, frequency can be written like 1 by 2 pi root of k plus A rho g by m. So looks like a little lengthy equation, but it's actually simple once if you understand the basic concepts and you take into consideration that to prove any equation of simple harmonic motion, first of all, we have to prove that the system itself is in simple harmonic motion. So we have done that. And then we have found an equation for the frequency of the system. That's it. Thank you for watching.